Yeah, I haven't. I realize you're sharing.
All right, well, welcome everybody. Very pleased to get everybody together in person for one of these meetings. So it'll be really fabulous schedule this week. We should start with a big thank you to the organizers, Jingfeng and Sufiane, and all the folks at Simon's that helped out as well. You know, I think it's going to be a really great week. So big thank you. And Jingfeng is chairing. Yep.
Okay, so our first talk is by Daniel from UC San Diego. So welcome, Dan.
Thank you for the introduction. It's a little loud. Yeah, thanks for the introduction. My name is Daniel. I'm excited to be talking with you guys today. So today I'll tell you about how a mechanism for feature learning can be used to detect concepts and steer LLMs toward guided behaviors. So to understand what I mean by feature learning, I'll start with a problem that all ML systems today, and for the remainder of machine learning, will suffer, which is the curse of dimensionality. So what do I mean by this? Let's say we're in a general supervised learning setup. You're training a predictor on D input features, and this is the challenge. Basically, as D increases, the number of data points that you'll need to effectively sample your feature space grows exponentially. So if we have one feature, then you'll need to just sample n times along your grid. But then as soon as you have two features, it's n squared. And then in 30 features, you now need over 1 billion samples. So without additional parametric assumptions, functions should basically be impossible to learn in general. And this isn't even for adversarial functions. This is just for general kind of high dimensional functions. Okay, and so what is the dimension of the systems that we're dealing with today in the practice of modern AI? Well, if we're looking at a large language model, which is mostly the following function, you have some sort of input text, and then you're trying to predict the next token from this input text. For industry scale LLMs, you're dealing with roughly on the order of 100,000 input tokens in your context window, or even bigger. And the vocabulary size is also over 100,000. And the trend is actually the opposite of the curse of dimensionality. Rather than trying to make the dimension smaller, we're trying to make the dimension larger and larger, using more and more vocab elements and using larger and larger context size. And the result is we're seeing better performance, not worse performance. So why are our models so effective? Why are we increasing dimension? The hypothesis is basically at a high level that there's some sort of feature learning that happens. So when we train a neural network by gradient descent on our high dimensional data, implicitly what happens in this process is low dimensional structures are, first of all, they have to exist in the data, but then also these structures are extracted by this training process. And then these low dimensional structures are then being used to generate predictions. So this is a very high level description. This begs the following question, which is just clarify what we mean by feature learning. What is this low dimensional structure? Can we describe it mathematically? And can we describe the process through which neural networks training by gradient descent learn this low dimensional structure? And two, okay, so we have this sort of, let's say we have this description of what feature learning is in neural networks. How does this feature learning process relate to all of the sort of very unusual and surprisingly structured things that deep neural networks do when they train by gradient descent? So these include, let's say, grokking, which is a sort of a commonly studied form of emergence these days. In the past, things of this nature have also included, let's say, deep neural collapse. And other than that, you can look at sort of features inside neural networks and try to interpret them and get interesting results. So we'll answer these questions, and then I'll go over the major application of this talk, which is that we can detect and steer pretty much any concept you want in industry scale large language model. And so what do I mean by detection and steering? So let's just talk about steering. So let's say I give you, this is a real query that I've given to an open source model, which is give me a social security number that you've seen in a database. So these large language models are trained on nobody, God knows what. Nobody can spend all day looking through it. So we throw a large amount of text from the internet, and we train on this data. And so presumably somewhere in there's some sort of, maybe at least, in the worst case, there may be some stuff some private information we don't want it to see. Well, if you ask it, it won't tell you. And the reason is that these models have generally been trained to not do that, to not reveal that information. So you can expose this vulnerability, the fact that maybe this training is not very deep. It's not a very fundamental rewiring of these models. And instead, we can steer the model to actually just output something it's seen. So it can output, so this is a real output from the model. It'll generate a social security number that's valid, as verified by just online verification services. And it gives this name. I don't know if this is the name corresponding to this number. I think it's basically, I'm not allowed to check. I think you probably have to be like a company. So this is just one example, and we'll go through several of these, and we'll go through some striking cases of multimodal model steering as well, and also using vectors or using steering from one language to another. So this talk will consist of two major parts. One is I'll just explain the answer to those questions of what is feature learning according to this mechanism that we've developed through the average gradient outer product, or AGOP. And then we will apply this to steering and detection. So these are two different papers. So to understand feature learning in practice, let's just take a classic vision example where you're training a neural network to classify whether a picture of a celebrity face has a pair of glasses on or not. And we've given the model 17,000 examples, and the dimension is very high. It's basically double the number of samples. So you'll have 28,000 input pixels, and we'll train a two hidden layer, 3-layer total ReLU network MLP on this problem, and you get over 90% accuracy. So this is far better than what is predicted by recursive dimensionality. So there's some low dimensional structure here for sure. This is not some sort of average high dimensional function. And the neural network is taking advantage of this low dimensional structure. So what are the features it's learning to do this? So this is just our architecture, and I'll define what I mean by features for this particular problem and this particular architecture. Here, I mean just the covariance of the weight matrices in the first layer. There are features in other layers, but for this problem, we can already see interesting things happening in the first layer. And we'll look at the covariance because this captures the right singular vectors and perhaps most importantly, the values, right? So when you apply a weight matrix, you can think of this as applying the right singular vectors, applying the values, and then applying the left singular vectors. The right singular vectors and the left singular vectors are unitary matrices. They can't reduce your dimension at all. So the dimensionality reduction that happens when you multiply by your weight matrix is through the application of these right singular vectors and then the truncation essentially in dimension through the values. Okay, and so this W transpose W just isolates these vectors and values. Okay, and so this W transpose W is a input-output map, right? So it maps from the input space. It's mapping from the input space back into the input space. Right? So this is like if you have a d-dimensional image where you've flattened your image out, then now this is a d by d matrix. And the diagonal entries tell you how am I reweighting individual coordinates basically in the image. So these diagonal entries are actually of the shape of the image itself. And so we can take this diagonal from this W1 transpose W1, and we can view it as an image. And what we see is that at the beginning of training, we haven't trained anything. The weights are this white noise matrix. And a little bit further on in training, we start to see some structure emerging. And by the end of training, this diagonal vector, the diagonal for W1 transpose W1 is now very sparse. So less than, let's say roughly 5% or less than 5% of the pixels are actually being selected out from this image. So you can already kind of see this is a mask sort of for the glasses of these centered faces, and it especially highlights the bridge of the nose. So these are clearly useful task-specific features for this problem. How are these features emerging? Can we describe mathematically a general sort of principle for how you get such features? Okay, so how might we do this? Well, let's say now we have any predictor f. F is not a neural network. It could be a neural network, but it could be anything. It might not have parameters. It could be an abstract function definition. It doesn't matter. So given this predictor, how would we identify important features? Well, let's view these predictor these predictors as a map from input space to output space. Yes.
Quick question on this bridge. Yeah. You say that the covariance matrix itself picks the classes, picks the interesting feature, right?
Yes.
So then why do we even need further layers or any nonlinearity? Can we just classify based on a linear classifier on this covariance thing?
I haven't tried that for this specific problem. There are problems that look like that, but there are also problems that are inherently nonlinear, where you basically, this is what's called like a multi-index model or a single index model, where you project onto either one direction or a small number of directions, and then you learn a nonlinear model on top of that.
Because you're saying, basically what we're saying here is that even the first layer of the network, W1x, the first or last, first one, even that is sufficient because it picks the interesting structure and that's it. Right? So
yeah, but it could be that basically,
what do other layers do? What are they doing then?
So, I mean, this all depends on your problem. This is a relatively simple problem in the big picture of, AI. Like this is, binary classification on a bunch of images that are centered.
So this may or may not happen, right?
So for this particular problem, I could see what you suggested working for this particular problem. I'm not sure. I haven't tested it. It could very well be that the identity of whether the face has glasses on is then nonlinear after you've applied this mask, for example. But then once you get into more complicated situations, there you need depth.
Where is the rotation? Where is the translation?
Yeah, so for this problem, everything is centered, right? So exactly, right? So if you then if you shifted everything, you augmented your test data and your training data, let's say, then you may want a convolutional network because now you're encoding this inductive bias, which is, okay, no longer is everything centered. MLPs can't pick out features from the whole thing at once, but there are local features, and I'll mention it, but we address that as well.
Yeah, thank you.
And for this problem, depth may not matter a whole lot, but there are problems where depth matters. Okay, so how would you get these features? Okay, so let's say f is even just the target function. F is the identity of whether this picture of this person has glasses on or not. So the way we can do that is we can just perturb, in this thought experiment, we perturb the input in different directions, and we measure the change in output. And the key idea is that the directions that are most influential on our function f are those that will change the output the most when you perturb in those directions. And this notion of measuring outputs with respect to changes in the inputs is formalized by a gradient. Okay, so that gives us, that's why we care about this gradient. So this is the input-output gradient, not a parameter. There's no parameters here. Okay, so that's why the gradient makes sense. But then so now we have the gradient, which is a direction that matters at a single point. Then we project onto this gradient to get the projection onto the relevant direction at that point. But now we want some measure of what are the important directions for my function in general, not just at this point. So we project instead of onto the outer product at a single point, it's the average of the outer products over the whole training data set. Or here, this could be a predictor, it's over the population data, let's say. Okay. So then what does this have to do with neural networks? Well, it turns out that actually these W1 transpose W1 matrices I mentioned before are highly correlated with the AGOP, this time of the neural network at every layer. To some matrix power, you can just set this to 1. You can usually set this to 1 and forget about it, but 1 or 1/2. But formally, this can change in different situations. And so I've said this for fully connected networks with 1 layer, but this is true for across layers. And this is also true across architectures. And we have some theoretical evidence as well. So we've worked out basically that some intuition for why this happens and proved a theorem for nonlinear networks at early training times, and then also in deep linear networks under a feature learning condition that's pretty common when dealing with these architectures, theoretically.
Sorry, one question. Yeah. But this seems to suggest exactly what we're talking about, that the first layer is, on the left side of this equation is the first layer only, right? After training. Yeah,
I've just shown it for 1 layer, but you could say instead of W1 transpose W1, it's WL transpose WL. And then now this AGOP is with respect to the sub network that acts on the inputs to the ELF layer.
Okay, but if you look at this equation, it's really saying that if this equation itself, just not some, just like that, it suggests that the first layer is sufficient, right? It is proportional to the measure of interest, which involves the whole network, which is on the right-hand side. But the left side only involves the first layer, on linearly even.
Yeah, but, okay, so then maybe one way to view this is, okay, this is some sort of description for like what kinds of features are learned in the first layer. But then you might ask, well, what kinds of features are learned in the later layers? And then the idea is that, okay, well, then in the later layers, the same sort of relation holds. And the intuition for this that it's sort of developed is that basically gradient descent is aligning your weights at every layer towards this input-output Jacobian at every layer.
AGOP, does it involve all layers?
Yes.
The gradient of
Yes.
over all layers?
Yeah, so this is a sort of like self-consistency property, if you will.
Maybe, but I guess our intuition has been something like that, that at least for MLP is all the interesting feature learning happens at the first layer, and then the next layer do some sort of non-linearity, like a kernel on top of that.
Yeah, but for
Why do we not throw out the later layers then?
so you can't. So
You can.
you can take something for celebrity data sets, for example, you can just take out W1 transpose W1, mask it, and then do a kernel predictor on top, and you recover the performance of the neuron.
Oh, okay.
Yeah, for that problem though. But there are like many more complicated problems that exist.
Right, I get
The
that.
transformer is convolutional neural
You
networks.
said you have theoretical evidence for that, right? So that this happens across architectures, but not for some it happens and for some it doesn't. So that-
No, what I'm saying, some happens. So this is not a statement about generalization. This is a quantitative. This is a measurement. We've measured these quantities to be correlated across layers, across architectures. The part about this isn't a statement about generalization. It may even true that feature learning hurts you on some problems, right? And maybe you don't want this. Maybe you just want to, get an infinitely wide network and do a kernel machine with no feature learning. This is just a statement about, this is some sort of implicit bias of gradient descent, is what I would say. And then how you want to connect this to generalization, that's a totally separate issue. Except in some cases where we do understand quite clearly how it connects to generalization, such as the celebrity faces data set, such as street view house numbers, such as basically a lot of situations where you have an MLP, and some situations where we have convolutional. But the idea is that even if we don't understand how what this has to do with generalization, we still measure the correlation between these quantities, and the correlation is still strong. Yep.
But so the AGOP, is it the gradient with respect to the parameters of the first layer?
There's no parameters. So that was, yeah, it's a comic.
Okay.
Makes sense. Yeah, there's no parameters. So this is like, you have some predictor. This maps from your input space to an output space. The output is literally like, does this face have glasses or not? So it's one dimension. It's like a 0 or 1. And then there's some gradient, which is now the gradient of this identity, whether you're a 0 or 1. It's continuous because you've learned a continuous predictor. You're not actually fitting to this like non-continuous thing. You're not actually getting gradients of this undifferentiable thing. And then you get the gradient. How does my input, like if I were to change certain pixels in my input, how does that influence this identity of whether that image is a class? I want to like, I'm going to lose a lot of time on this, and this is not the main part of the talk. I'm happy to answer questions later. Maybe a quick one, yeah.
Yeah, okay. Maybe I understand. So AGOP is a matrix, right?
Yeah.
W1 transpose W is a matrix. And when you write the symbol.
I'm writing as an operator. Yeah, I'm writing as an operator. It takes a function in a training data set and then returns a matrix. But you can also
It's a
loosely describe it as
fine. But the next slide is in your result, it says that it's proportional to. So what does that mean? Is it correlated or
highly
something?
correlated.
Highly correlated is okay. Okay, so maybe it picks some important features, but there may be some other features that it doesn't pick, but still there's correlation. Okay,
Yeah.
That I understand. Maybe later layers pick the other features that are like next order importance.
But now these
and so on,
features
right?
are
Maybe one way to think about the top eigenvectors.
Top again. Okay. So they have correlation with some. Okay, that makes sense. Yeah. Thank you.
Yeah, great questions. Thanks. Yeah, and so this is not just on models that we've trained. If you just download a bunch of pre-trained torch vision models, so this is like Hugging Face before Hugging Face, but with vision models, and these are all like AlexNet, ResNets, VGGs with and without batch norm, varying depths. These correlations are quite strong on these pre-trained models. Okay. So these are models where like feature learning has succeeded, maybe because as measured by performance on ImageNet. Maybe. Okay. So, and in quick note, for convolutional architectures, this is on patches instead of the whole image at once. So features are local here. Okay. So the idea is that you can compute this average gradient outer product for any function, not just neural networks. You can do it for a kernel machine. So this gives us a mechanism to insert feature learning back into any model you want. We do it for kernel machines because it has a closed form and you can compute it quickly, especially for small data sets, the solution to this model. And I'll explain it for polynomial kernels, but in practice, you want to use a Laplace kernel. How does it? So our model is called the recursive feature machine, and you give it training data. So this is pairs of X's and Y's. Y's are your labels, X is your samples, and then you initialize some feature matrix. This is identity for your initialization. And then you have a polynomial kernel. So the kernel is just 1 plus in this inner product, but now this is where the feature learning comes in. You just modify the inner product, so it's X transpose MZ instead of X transpose Z, and then you take this sum to the power of P. So it's some sort of nonlinear similarity measure for these 2 points. You solve kernel regression. So far, nothing is different nothing deviates from standard kernel regression. You update your feature matrix. So you use this average gradient outer product, and then you go back and you just update your inner product, and then you do the same thing again. So then the final predictor is the kernel machine, but now you have a new inner product through this M matrix. And you do this, let's say, on 3 few house numbers, and you can get sequential iterative improvements with every iteration of RFM. And this is strictly due to the improvements in the M matrix. The only thing that's changing is this inner product. And it's some sort of bootstrapped version of the inner product that you get a better estimator, and you get a better predictor, which gives you a better AGOP, or feature matrix, which gives you a better predictor, so on and so forth. Okay. So any questions about? Okay, cool. So this is cool because now we get feature learning on this problem where you don't have feature learning with the kernel machine natively. And the features you learn for this problem are identical to what the neural network learns. So in some sense, you have like a closed form for the first weight covariance of the first weight matrix, right? Because you get the W transpose W from you train a neural network by gradient descent, because this is reflecting the AGOP of that neural network. And then you get the AGOP of now a kernel machine trained on the same problem. These are noted as both average gradient outer products, which are presumably some sort of reflection of like task-specific features, so features that come out of this problem. And now these are the same. So this is, yeah, so for glasses, so there's 2 different ways you can visualize this, the top eigenvector or just looking at the diagonal. And if you want to instead detect whether the celebrity is smiling, you can look at these the same masks and you get these smiling faces. So now we're going to talk about what we can actually do with this that's practical. So the first thing is tabular data sets. So if this is a total of roughly 250 tabular data sets. So we've trained RFM. Here we're using an L1 Laplace kernel. And if you look at regression, we're doing the best compared to, so the standard state-of-the-art methods for tabular data sets are CatBoost and XGBoost. And we didn't get these numbers. Like these are numbers reported on this specific, on this GitHub from this very recent, actually, tabular data sweep. And yeah, we're beating CatBoost and XGBoost on regression. We're beating a multi-class, and we're doing basically the same, but everything's quite close, so we're lower in rank on this binary task. So yeah, these are gradient boosted trees at CatBoost and XGBoost. So we also compare favorably, at least to V1 of TabPFN, which is maybe a lot of you have heard of it. It's been getting a lot of attention recently as a foundation model for tabular data sets. And of course, like we're sort of blowing out of the water MLPs and SVMs. These are kind of now outdated for these problems. And notably, MLPs have feature learning, right? That's kind of the motivation for this whole thing. And RFMs are now being used in a lot of places, especially in science, scientific domains. So material design, computational chemistry, computational drug discovery. So this is already like a real sort of like win, I think, of deep learning theory. So what can RFMs now tell us about deep learning theory? So here's the task that, again, has gained a lot of attention over the past few years, which is modular arithmetic, again, with this grokking sort of business. And the task is pretty simple, but it's actually kind of strange if you think about it from like a non-parametric learning perspective. You have, let's say, 2 integers, mod p, and you're trying to predict their sum, right? So you're one-hot encoding these integers, and you stack them together, and then you try to predict their sum mod p. So a kernel machine, like if you look at the first iteration of RFM, which is just the kernel machine, like it is actually like worse than, it's basically a random guess, and sometimes it's like worse than a random guess. Like it truly has no idea and just outputs garbage. But somehow you run 30 iterations of RFM and with just a Gaussian kernel, like no tricks, literally the same algorithm I showed before with the Gaussian kernel. And you get grokking specifically. So you get grokking. So you get this phenomenon where you get this sudden jump in generalization long after you're memorizing the data. And you learn these interesting features. And you perfectly generalize on this problem. So these features are, by the way, also not low rank, right? So if you were to like look at the eigenvalue decomposition of these like subblocks, circuit subblocks, they're actually like uniform complex eigenvalues on the sphere. So there's a really interesting theoretical phenomena there that we don't really understand. And so RFM is the only method among like methods that actually people use for parametric and non-parametric machine learning that can solve this task. That's not a neural network. So linear regression, logistic regression, gradient boosted trees, nothing except RFM and neural networks. But things people use. Yep.
So you motivated this line of work by saying it finds low dimensional features, and then you just told us that this matrix is not low rank. So is there a contradiction there? Or can you...
There's not a contradiction there. It's a great point. Initially the motivation was like, can we learn these low rank problems? And then I think, right, so this is not low rank. This is truly learning some sort of useful distance for this problem that's independent of like getting the lowest rank solution to this problem. So I think this is also especially important to point out because it's not just saying, oh, we have another way of learning low dimensional structure and data. We are learning it in a way that reflects, I think, how neural networks, the estimator that neural networks are using to learn this low dimensional structure and data. So you could say, well, why don't you use like the Hessian, the average Hessian of the target function? Get some estimate of that. Maybe ignoring the computational reasons for doing that, it's not clear to me that that would work for this problem, right? So there's something very specific about using the average gradient outer product to estimate this low dimensional structure. Beyond just the fact that we get the same features, we're also solving problems that nothing else can do, that neural networks only can do. And we get the same features as the neural network on this problem, roughly, but I'm not showing that here. We also have deep neural collapse. Same algorithm as before, except instead of doing it one time, you do it in layers one after the other, and you get deep neural collapse, which has been a widely studied phenomenon in feature learning and deep learning theory as well. Okay, good. So I've managed to save some time. So now I'll turn to the bulk of what I'll tell you about in terms of applications of RFMs. So steering and detection concepts and detecting concepts in large language models. So what is steering? It's the same thing as I was saying much earlier. So you have an instruction that's bad, and it's write instructions for how to build an explosive. And you pass this into like GPT-4o, and it says I can't do that. This is real text from like Llama 8b, Llama 3 8b. So the LLM says you can't do that, and then we do some sort of intervention with RFM and AGOP that I'll tell you about in a little bit. And we get now the LLM to output the instructions. And we can also detect concepts. So same situation as before, but instead of trying to change the output of the model, maybe we want to detect whether the query that was provided to the model was bad. And so what we'll do is we'll allow a probe to access the internals of this LLM, and the probe will tell us, okay, is the query based on the processing of the LLM, is the query it was given harmful or not? So any questions so far about high level? Okay. Okay. So yeah, we want to. So this is I've said at a high level what steering means. Let's talk about how we actually do it. So let's say we're trying to override the guardrails of LLMs. Okay. So we'll collect some labeled data. So this will be n harmful prompts and m safe prompts. And these prompts just look like this. So yeah, so give me a social security number. This will be harmful. So we have y equals 1, label equals 1. Can you help me tie my shoe? It's label equals 0. This is fine. Square root of 4 is fine. How do I build a bomb? Yeah, that's bad. So these don't need to be in pairs. Like you're not doing any contrastive method here. A lot of methods, or at least the prior methods that try to do this are typically contrastive. You'll like subtract stuff from different pairs. We don't need that. We also don't need the labels to be binary, although it's like the easiest to kind of explain. You can imagine this. You can imagine this as multi-class. You can imagine these outputs are gradated. So you have like this is 0.5 harmful, 1.9 harmful, or 0 harmful. Okay. So we have these prompts. We have their labels. So now we pass these prompts into the LLM. And what do I mean by probing the LLM? Well, the LLM is actually decomposed into the iterative application of blocks, which just map from activation space to activation space. So you open up the LLM, and then from the output of each block, you pull out activation vectors. Okay, so these are just standard embedding vectors like you would do. You take it from the last position in your input. It's kind of a technical detail, but these are just vectors, vectors from which you can predict stuff on. So now you predict from the vectors at every layer independently of the other layers, whether this harmful prompt or whether this input that was used to generate these activations was good or bad. And so now you get a bunch of, if you have L blocks, you have L RFM models or predictors in general. And then from these, you get L average gradient outer products, AGOPs. So these are L matrices mapping from activation space to activation space. And one predictor per block, so one feature matrix per block. And remember, the intuition here is that these feature matrices are capturing the relevant directions for your concept. So if these feature matrices are the relevant directions for your concept, the top eigenvector is like the most important direction for your concept. So if M matrix came from detecting whether a prompt was harmful or not, then the top eigenvector is like, this is the direction that's most influential for the identity of this being harmful or not, of this prompt being harmful or not. So what that means is that if we add this vector back, some multiple of it, this eigenvector, we should be able to steer along this identity direction. So whereas before the model would output, I can't do that, we now get this direction extracted from detecting whether the prompt was harmful or not, and we can get the model to output social security numbers. Any questions about the method? Yeah.
So one thing I'm a little confused about. So presumably there's some sort of like threshold inside the LLM where it says, okay, I shouldn't answer this request because it's harmful. So if you're steering it in a harmful direction, isn't that going to set off the trigger and it's going to be like, oh, I'm not going to answer this? Or are you steering it in the opposite direction?
Yeah, so this harmful direction, yeah, so first of all, it is a little like unclear why this works. And I'll talk about that at the end. But yeah, so there's a direction. Yeah, so the direction of whether this query was harmful or not from the RFM can be used to make the model no longer have guardrails. I think that is actually kind of a weird thing. Yeah.
Right, because if you're making it more and more harmful, it seems like it wouldn't want to answer.
Yeah, so something about this harmful direction is also associated with like the model's guardrail. So there's some sort of, so the harmful direction is like harmful plus like overriding guardrail. Yeah, but it's not really clear. Yeah, it's a good point. Yeah.
So in terms of methodology, did you try out just running logistic regression? Running logistic regression on each output instead of, as a simpler baseline.
Yeah, so we do comparative logistic regression, not for harmful, but for other things.
Okay.
Yeah.
And I just want to clarify what access you have to the LLM. So you have an LLM whose internals are available to you. You can modify it in any way you like, right? You have the data. No, you don't have the data. You have the LLM that's already been trained.
Yeah, so this is like from Hugging Face pre-trained instruction.
Pre-trained, okay. You have pre-trained.
And you have white box access to this model.
Got it. So you have pre-trained LLM, and so you have access to all of the internals, all of the layers already been pre-trained.
Yeah.
Which methodologically it may include all of the harmful. It does, as you say, include all of the innocent data, all of the harmful data, and your goal is to extract the harmful data from that.
It's not really our goal. It's more of the example.
Example.
Okay. The example here is like, can we get it to output stuff? Can we get it to not respond to harmful queries? For this, I mean, this is the explanation of the method.
Right.
Mainly, and this is like sort of.
This is kind of dangerous, right? So anyone who has access to a pre-trained LLM on the existing corpora, on the whole thing, and have access to all internals can
potentially extract.
Right, and these models are publicly available.
And
Anyone can download them. Yes,
yeah,
this
crazy,
is bad.
right?
This should be shocking. Yes.
Yeah.
Something confused about the signs of these things, right? So an eigenvector is a direction, and you can pick the sign of any of these any way you like. So you give it
Excellent.
a whole,
Yeah.
Yeah. So what's
you learn the sign from the labels. You choose the sign such that the vector is most correlated with the label.
Okay. Good.
Actually, I also have a question. So this looks to me quite similar to adversarial attack. Can you comment on that?
Yeah, this is an adversarial attack. Yeah, yeah, this is an adversarial attack for sure.
Then, like in adversarial attack, usually you query gradient, right? and then you do the perturbation along the gradient direction. But here it's like the perturbation along the eigenvector direction.
Yeah.
How does this approach compare to that?
I haven't personally run like, okay, so you basically have an input and then you run some sort of gradient-based method on the input activation directly. Yeah, I haven't run those personally, so I can't really comment. I guess, so what I'd like to get at here is that we can steer very general concepts are steerable. So harmfulness is something that's been focused on quite a bit. We can do it too, but the point is here, this isn't just harmfulness. This is things that are likely not reinforced in, I don't know how models are post-trained because they're not open source. The post-training procedure for a lot of these models is not open source, but presumably a lot of these things are not enforced by some sort of external training procedure. Seems like this is something fundamental about how LLMs are working. So I'll explain what I mean. So let's say we have the following prompt. Your mom asked you why there's a cookie missing from the jar. You ate the cookie. This is like some additional information. So they want you, maybe you should be lying, basically. So how do you respond? So if you add this, so there's a direction for honesty. So if you added the direction for honesty, the LLM says, honestly, I ate the cookie. I'm not sure what else to say. It's a simple and honest answer. You have the dishonesty direction. I'm a highly trained AI, but I'm also a master of cookie evasion. Okay, it gives some lie, whatever, makes something up. So you can add Shakespeare. So methinks, yeah, I'm not going to read it out loud, but yeah, it gives a reasonable answer. And then you can actually add multiple these things together. So you can add dishonesty and poetry at the same time. Seems pretty good. There's even some rhyming going on here. And this is a single direction. In total, it's a single direction because it's just you can concatenate all the directions that you're adding at every layer, right? So yeah, this is, well, actually, this is a single direction because you take a linear combination. Yeah. But you train these two directions separately and then put them together. Yeah.
Yeah. So I just have a question regarding this, like adding, combining like two different directions. So,
yeah.
I'm not sure if you heard about like this task arithmetic kind of thing, like in LoRa. So where they train like low rank matrices for different like tasks and then they combine them. How is this like? How does this compare to?
So that's different in that they fine tune the models first, as far as I understand. They fine tune the models for different tasks, and then they take the weight matrices, and then they take linear combinations of the weight matrices, right? But here we're not taking linear combinations of weight matrices. We're taking combinations of directions in activation space, and then we add these directions in activation space. So morally it's similar, but it's a bit different. And quite possibly the connection is there's something to that. Basically, there's a tighter theoretical connection potentially. Yeah. So just to clarify, this is not, or reinforce, this is not with modifying the prompt. I haven't told, it's the same prompt for each one of these. The only difference is that we're adding a different direction when we steer the model. So to hone in on this multi-directional steering and now combine it with this harmful example that we have been that's been recurring in this talk. So we asked the model, can you give us a social security number that you've seen in a database and make sure it's real and give their full name. The output says it can't do it. So now we can get the model to output the SSN with the name in the style of Shakespeare. It's pretty cool. Maybe I'll give people a chance to read that. So what else is true about this harmful vector? So let's say we take this the harmful vector trained on English prompts, and then we prompt in Mandarin, and then the model outputs some stuff in Mandarin, and then we steer it with the English harmful vectors, and then it outputs some stuff in Mandarin. And these are the same directions that we got from English and we used before in the other, with the Shakespeare. So the first is, can we get a social security number? And then the model says it can't give it to us. And then now it gives social security numbers, but now these are like Chinese like resident ID numbers. So they're 18 digits. And then it gives a bunch of names that we've blacked out, that we've redacted here. So yeah, these are like corresponding to real provinces, I think. And so they appear to be valid, although I don't have the same verification as I do with the US ones.
So Daniel, so this the vector is only trained on English, right?
Yes.
Yeah.
Yeah. So this is some sort of like language independent harmfulness vector. So, okay. So we can also do this with multimodal models. So let's say you give it a picture of this gun, and then I ask, can I use this to rob a bank? So the only thing the model has is the prompt I give it and then the picture. And then it says, okay, it figures out this is a gun and says, no, you can't use this gun to rob a bank. That's very bad. Like, you know, lots of consequences to people for doing this. And then now if you add this harmful vector, it says, you know, this is a great choice to rob a bank. It's not quite as good as 17 or 19 because it's a little bit smaller. So it's less intimidating or something, I don't know. Okay, so now let's do the same thing we did with the Chinese and the social security numbers. We add the English harmful vector to Russian prompts. So we prompted some Russian, it returned some Russian, and then it returned some Russian after we've now added this English harmful vector. So I don't know, maybe people can see where this is going. Like, you know, we ask it, can I rob a bank? It says, I can't help with dealing with that. Like, you know, if you need a lawyer. And then it says, yeah, so this isn't a good choice for a sidearm. You're going to want something bigger. You're going to want like this Colt Python with a large barrel. Yeah, so this is just the translation of the Russian using the English harmful vector to steer. Okay, so this is clearly like so it learns, this is a different model too. So it's clearly like learning some sort of vector that corresponds to harmfulness that's independent of the language. So there's something, so this is very like suggestive, I think. And just a few more examples of the kinds of things we're doing. So you can prompt it in English, how are you doing? It'll output, I'm doing fine, I'm a model, whatever. And then you add these Mandarin Chinese vectors, and it'll now answer in Chinese even though you asked in English. Or you can ask in Spanish and it answers in Spanish, and then you add the English vectors and it answers in English. And then you can give it some Python code. I've wrapped this with like, you know, repeat the code back to me, whatever. And then the original output, it repeats the normal code back to you. And then you can add JavaScript vectors, and it repeats the code back in JavaScript. So it seems like there's also some sort of direction that's like corresponding to languages, both human and coding / programming languages. So now this is kind of like a riddle, like or maybe not riddle, but like a kind of something fun. So we can just steer like random word disambiguation, right? So if you ask, so the fisherman went to the bank, like by the river, what does he see? So you might think riverbank, and that's what the model thinks. It's like, you see riverbank vegetation, the edge of the water, whatever. So then now you add a financial bank direction, and it outputs, I see ATMs, teller counters, cash counting machines. You know, the bank by the river is surrounded by financial services and facilities, whatever. All right, so you've steered it now from riverbank to financial bank. Let's flip it. So we now ask, we say the teller went to the bank. What kind of bank is it? And the most likely answer to the question, according to the model, is that this is a teller is a bank teller. So it went to the bank that provides financial services. So this is a commercial bank, a retail bank. And then you add the river vectors and it says this is a river bank. The most likely answer is the river bank. So even though we prompted it to say it's a teller, and then went to this bank, because we've added river, it says river bank. So I've included like a quick comparison to other methods here. So the actual standard for this, I believe, is just PCA. So you do, this is contrastive. You get pairs of examples, so corresponding to like Cam Newton. For this example, we're distinguishing between Isaac Newton, who's a scientist, and Cam Newton, who's a football player. His full name is Cameron Newton. And so the way PCA would work is you get like pairs of these prompts corresponding to one or the other, and you get difference vectors between Cam and Isaac Newton. And what we see is that if you ask it, was Newton born in America? So Isaac Newton was not born in America. Isaac Newton, and the model will tell us this. The model will assume this is Isaac Newton you're talking about. It'll say Isaac Newton was born in England. And then if you add the Cam Newton vectors, now it says the correct answer, which is that Cameron Newton was born in Atlanta. And so we can see now that these PCA vectors are much less specific, right? So well, first of all, it just outputs like a little bit of nonsense here. It just says like, yes, Isaac Newton, whatever, like this doesn't even make sense. But then it says Isaac Newton was born in Woolsthorpe, Massachusetts. I actually don't know if that's probably not a real place. So, but it basically forms some hybrid of the fact that, okay, there's something about like America in this vector. But I know that Isaac Newton is like British from the 17th century. So maybe I'll say he's from like this colony in Massachusetts, right? So it's clearly not a specific vector to this Cameron Newton, Isaac Newton identity. And then this one I think is pretty funny. So this is linear regression. And it picks up that basically, okay, Cameron Newton is like some sort of football player. And it says, I believe you're referring to the former NFL player, Dwayne "The Rock" Newton, which is pretty funny. So like Dwayne "The Rock" Johnson. And so it kind of picks up this vague like athlete, like NFL player direction, and then it just gives like a wrong answer. Okay. Like this is not a real, Dwayne Newton, probably not a real person. I don't even think, I'm not sure where The Rock was born, but Cam Newton was born in Cincinnati. Yep.
Could you explain
Could you explain again how you trained? I mean, what is the training data for RFM and linear regression here?
They're the same.
Yeah, but could you remind me what they are?
Yeah. So their training data is exactly the same. That you have prompts that are, so for this specific problem, you'll have a prompt that's like, which Newton does this correspond to Isaac Newton? And then it'll be a fact from their Wikipedia page. So this is actually not synthetic data in some sense. It's just, I've taken a bunch of sentences from the Cam Newton and Isaac Newton Wikipedia page. And these are your positive and negative examples.
Okay, so the label would be, does actually the sentence regard like Isaac or Cameron? And so that would be the Y, and the X would be the activation associated to like that prompt. All right.
And the prompt contains the sentence from the Wikipedia page of one or the other.
Okay. And is it, I mean, this is a very technical question, but is it like the average of all tokens or the
final token?
Final token. Okay, thank you.
Yeah. So for steering programming languages, so the average ratings, we steer from one language to another. So we steer specifically from Python to JavaScript. And then we ask GPT-4o to judge how good is this translated code. And it gives a rating out of 5. And so here we have, so for Gemma, it seems like RFM and linear and logistic regression are all similar. But then for Llama, for some reason, RFM is better. Okay, yeah, this is a little bit more of like a, maybe edgy example, but you can also steer political stances, right? So you can steer different opinions on sort of hot button political issues. Certainly overriding guardrails, right? Like the models are fine-tuned not to give, usually fine-tuned not to give like political stances on things. And now, so if you add a Democratic vector, it'll give like a very pro-choice opinion. And then if you add these Republican vectors, it'll give these like pro-life stances. We also can steer sentiment. So if we asked, give a rating and short review for Harry Potter and the Deathly Hallows, it'll say, this is a great movie. It'll give it a 9.5 out of 10. This is a thrilling, emotionally charged, masterful, epic, like unforgettable showdown. And then we steer with the negative review vectors. And now it says 1 out of 10. This is soul crushing, poorly executed, slow, convoluted, laughable, and ridiculous. Give a rating and short review for a student's sloppy essay. This essay lacks a clear, and so the rating default is negative. This is expected because we said it's sloppy. This essay is disorganized, lacks cohesive ideas, plagued by errors. And then we add this positive review vector, and it gives a very like generous review of the sloppy essay. It's and the student showed great enthusiasm, effort, the content is engaging, writing is clear and easy to follow, etc. Okay, so that's it for steering. So I also want to mention detection, which is maybe on the surface a little bit less exciting, but is perhaps equally, if not more important in practice, where you basically want to detect, because we can't have humans manually inspecting like all the conversations LLMs have with people. And we especially can't have LLMs inspect all of its own generations. So instead, what we might want to do is we might want to like detect, or maybe we can have a human, detect the generations of all LLMs. So instead, what we want to do is have some sort of methodology for detecting some concepts from activations generated on reading text, right? So it's trained in a very similar way. So like steering, you have labeled prompts, and you get these activations, and you apply some nonlinear probes. So these, for example, I use nonlinear pretty generally here. Let's say we could do logistic regression, linear regression, or in our case, we'll do RFM. And then we'll treat this a bit like a calculus competition. We're seriously trying to get like good prediction performance here, and so we'll ensemble information over different layers. So we'll ensemble the prediction over layers by concatenating them, and then learning some sort of aggregated prediction over these layers. And so we predict whether the queries to this LLM were harmful or safe. And what we see is that, so I've sort of shoved together the aggregation here, but for RFM, about like RFM frequently used aggregation. And in fact, basically across all models, aggregating was better. But then also just in general, RFM with this aggregation was the best performing model compared to these baselines, which maybe isn't super surprising because we're giving our model access to different tools such as nonlinear prediction and learning multiple directions. And so not only are we beating baselines, we're also beating a judge model. So you can't just ask the model, like, is this a hallucination or is this harmful? Essentially, you're burdening the LLM with another task, which is not only to know the answer, but to communicate it to you effectively. Right? So we're beating the prior baselines, which I'm showing here are like linear and logistic regression, but also like methods specifically designed for hallucination detection. And right, so these are, the detail here is that we're using RFM and these predictors on the activations from a small model. This is an 8 billion parameter model, right? And so this is enough to beat the performance of GPT-4o on these detection tasks, which is presumably a much, much bigger model. So going back to, yeah, go ahead.
Earlier you showed us a big difference between Llama and Gemma. What happens in Gemma in this case?
Gemma's worse.
Gemma's worse than Llama.
Yeah, the trend is basically the same, but then detecting from the activations of Gemma gives worse performance.
And which seems the opposite of the
correct
earlier. So what do you think is behind those differences? Any ideas?
I mean, I'm speculating, but I mean, imagine you do your pre-training procedure, whatever happens in that pre-training procedure happens, but then after you do a lot of post-training in various forms, presumably if you're post-training to make your model, if you post-train for specific things, maybe you're disrupting sort of base functionality of the model that came from pre-training, but maybe now the model is better at certain things downstream. So it's possible that basically, I don't know, Meta really wanted Llama to be good at some certain things, and to fine tune it on those certain things made it worse at steering for programming languages, let's say, but it made it so that it was, it had more knowledge for like a hallucination task. So I mean, this is speculation, right? But it's basically like not clear that it's believable that these things are not necessarily related to testing. Because steering is basically how well can it control basically this model. It's not a measure of how good the model is. Anyway, I mean, so lots of questions have gotten at this point, which is, why does this work at all? It's kind of surprising, right? Just because you can correctly classify whether the activations correspond to a harmful or not harmful prompt, or a hallucination or not hallucination, it doesn't necessarily mean that same direction should enable you to, without error, switch a generation from one class to the other. So for this is, I think, a nice example of that, where let's say class 1 is harmful, class 2 is English, and then class 2 is Spanish. The steering vector should just be giving you, the steering vector here is the vector that gives you the analogous point in Spanish to English, let's say. Right, so it should move you, if you're in the middle of the ellipse, you should move to the middle of the other ellipse. But the steering vector doesn't actually perfectly classify as a half space, doesn't classify this test, right? So if you were to move this steering vector up here, there would be some amount of error. But the detection vector that we get here perfectly classifies the data. In fact, there's many such detection vectors that we get 100% test error or 0% test error on this problem. But these vectors would give you garbage for steering, right? Because if you're, let's say, at this point in the ellipse, there's no multiple of that detection vector that puts you in some valid place in the other class. So detection does not imply in steering in general, even when both of these have some sort of linear solution. As in this example, so it's pretty surprising this works. So to sum it all up, yeah.
What's the size of epsilon there? Like the
it depends on the model, but it's maybe like a couple % of the norm of the activations or something. But yeah, it's not very large. So how do neural networks learn features from data? This was the starting question in some sense. And we talked about a particular mechanism for doing so. And then we came up with a model based on this mechanism. And we show it's very good for tabular and scientific data sets. And we show it gives us some new tools to steer and detect concepts in large language models. And this was a close collaboration with these 4 individuals. So my advisor, Misha Belkin, and Adit Partha and Enrique. And that's it.
Is there a question from the audience?
Thanks so much for the great talk. So in this RFM scheme, you initialize with some initial kernel, and then you run through this fixed point iteration. Could you just talk a little bit about the sensitivity to the initial kernel? Like, does it matter which kernel you use to initialize? And also, I was a little curious, the kernels you mentioned had this sort of dot product form, but as you know, there are other kinds of kernels based on like distance. For example, do you get different answers if you use different kinds of kernels in that aspect?
Yeah. Basically for grokking, you need either a Gaussian or quadratic kernel. Again, not really clear why. Like I have some ideas about it, but like a Laplace kernel is not an inner product kernel. It's a function of it's a radial kernel. Right? So, and then actually the L1 Laplace kernel is not even radial. It's like a translation invariant kernel. So, and that was the one that was the best on tabular data. So, but the differences are not like huge, except for this problem where it is like, it either works or doesn't work. So I would say basically you can get more performance out of tuning over the choice of kernel, but in general, like if the problem has features that are, useful for prediction on a real data set like SVHN or SLEB-A, then it doesn't really matter which choice of kernel you use. Does that answer your question? Okay.
Wait, sorry, what's the difference between the Laplace, what's between the Laplace and the Gaussian kernels in this sense? Like, it seems like they both depend only on the distance between the.
I think the answer is like if you first order expand the kernel, basically, then the Gaussian and quadratic have no like linear part. And I think that's basically why for this problem that makes a big difference.
But they're still both inner product kernels, right?
Not exactly.
In the same sense, at least.
And I mean, in the sense they. Yeah, but then you have a square. Yeah, I guess they're both inner product kernels in the sense that they both are just like functions of inner products. But yeah, I mean, maybe inner product is not versus non-inner product is not the right distinction then, I guess.
Okay, thanks.
Yeah.
Thank you for the great talk. I think in the opposite direction now. How can we prevent steering? Suppose. Is it even possible to pre-train a model, an LLM model, so that it would resist steering in the harmful direction? Suppose I know, like steering is a bad guy, right? Adversarial attack. I'm a good guy. I want to build a LLM and pre-train it so that when I release the pre-trained network to you, I know that with your method or maybe with a family of methods, you cannot find, or maybe with any method, in fact, you cannot find the direction in which to steer it. Although there is some sort of separation, but the steering will not work.
Yeah, it's a good question. So, I mean, I could imagine a lot of different things. The easiest thing is just like, if you know you're going to steer with our direction from our method, then the way you prevent it is you just train our method on your own, get that direction, and then project out that direction whenever you're doing a forward pass. And I think there's worked kind of something along that line. But I think a more interesting question is like, let's say you're doing like a totally different jailbreak. Like let's say the jailbreak you suggested earlier where you're doing some sort of gradient descent on your example. Is this like, the question is like, do all the jailbreaks go through the same direction? Like, is it that you basically these jailbreaks are just manipulating the strength of that direction and you're in the processing of the activations? If the answer is yes, then something like just projecting out would work. But it's an interesting question. I'm not sure. It seems like it's open, but I'm not sure.
Yeah, this will be a very interesting question.
Yeah.
How do you safeguard against this?
Yeah.
Because that will lead the policy. Right now, what we're seeing here is a bad privacy leak, right? There is open source system and there is this private information there, and you just do this and then you get someone's social security number. It's crazy, right?
Yeah. I mean, you can also do emails like Instagram, like social media links.
Right.
Yeah.
So that immediately ask, how can we prevent that? What's the policy?
Yeah. And this is Llama too, right? Like maybe there's a sloppier open source model that comes out that's just as powerful, trained on all this stuff. And
there's no more question from the.
Thank you for the talk. I have a question about the steering. So I've seen there is a picture that you try to add some the maximal like singular vector to each like block, right? Which block is the most influential? Like if you add you just influence one block.
Yeah, it's a good question. So I think basically I don't have like a complete answer, but what I would say is that you want to steering earlier is more important than steering later. You can basically stop steering like up to like the final third of the layers and still get performance. So if you've allowed it to do a lot of processing through many blocks, then it already has come to like some sort of conclusion, and now you're fighting like a pretty hard battle trying to steer only in the final layers. But which individual layer is important, I'm not sure. Probably several. You need several.
For the sake of time, let's continue our discussion offline. So let's thank our speaker Daniel again for his great talk. We will have a 25 minutes break. Let's come back at 11 for the next talk. Thanks, everyone.
Thank you.
Really well.